and extend that to finding powers and roots. So where are we at? 6.5 part 2. All right. So let's remember what we came up with for how we, if we have a complex number in trig form, how we multiply them. So we said if z1 was r1 cosine theta 1 plus I sine theta 1, and z2 was r2 cosine theta 2 plus I sine theta 2. In order to multiply these, we went through a nice little multiplication, and we ended up using a trig identity, and we found out that this was r1 times r2, and then we add the arguments. Made it really nice and easy. Plus I sine theta 1 plus theta 2. So we multiply the moduli and add the arguments. And then to divide z1 divided by z2, we divide the moduli and we subtract the arguments. So multiplication and division are very much simplified in trig form with complex numbers. So now what we're going to talk about is powers of complex numbers. And we're just going to use this. So what if we wanted to do z1 to the n power? So instead of z1 times z2, we have z1 times z1 times z1 times z1 n times. So we just apply this over and over and over again. So how do we write r1 if we're multiplying the moduli? How do we write r1 times r1 times r1 times r1 n times? r1 to the n. And then we're doing theta 1 plus theta 1 plus theta 1 plus theta 1 plus theta 1 n times. So how do we do that? Theta 1, so we're adding it n times rather than multiplying it. So how do we write repeated addition? Multiplication. So it's going to be cosine n times theta 1 plus I sine n theta 1. We just multiply the angle by n. So to find the power of a complex number in trig form, we raise the modulus to the nth power, so that's just raising a real number to the nth power, and multiply our angle by n. So imagine how when we worked with complex numbers in the past, imagine doing something like 3 minus 7i to the 7th power. So you would have 7 of those parentheses, and you would have to multiply and combine like terms, and I squared equals -1, and then combine, and then multiply again, and do that over and over and over again. That's a long, complicated process. With this, we can write this in trig form, multiply the modulus, raise the modulus to the n power, multiply our angle by n, and
how do we solve for theta with 3 minus 7i?
Theta, just like we did on the homework last time, tangent theta. And we'll do an example here. Tangent theta is minus 7/3. So theta would be the inverse tangent of minus 7/3.
Okay, and then we just plug that in.
Plug that in, multiply it by n, multiply it by 7.
Okay.
Plug that into your calculator, find the cosine, find the sine, and you're set. All right, so let's look at an example of this. Let's say we wanted to find minus 2 square root of 3 minus 2I to the 5th power. So in order to do this the way we knew before, we'd have to multiply these. We'd have to write out 5 of those parentheses and multiply everything together. FOIL, simplify, over and over and over again. So the first thing we're going to do is write this in trig form. So to write that in trig form, we're going to find the modulus. So R equals the square root of minus 2 square root 3 squared plus negative 2 squared. So we get the square root of, let's see, that's 4 times 3, right? 12. Plus negative 2 squared is 4. Square root of 16, which is 4. So this one works out nicely. And then let's find our angle, tangent theta. Hopefully this is a mechanical process by now. We did it with vectors. We're doing the same thing here. Tangent theta is minus 2 over minus 2 square root 3, which is 1 over square root 3, which is square root 3 over 3. What quadrant are we in here? 3? Third quadrant. So we need a third quadrant angle whose tangent is square root of 3 over 3. And remember we said, is it pi thirds? We said the tangent, one way to remember which is which, the tangent of pi over 3 is square root of 3. So this is going to be related to not a third fraction, but a sixth fraction. So it's our third quadrant angle with a sixth fraction. Theta equals 7 pi over 6. So what we have here is minus 2 square root 3 minus 2I to the 5th is 4 times the cosine of 7 pi over 6 plus I sine 7 pi over 6 to the 5th. And to do that, we're going to say this is 4 to the 5th times cosine of 35 pi over 6 plus I sine 35 pi over 6. And hopefully we can find the cosine and sine of 35 pi over 6. 36 pi over 6 is how many pi's? 6, which is coterminal with what angle? 360, 0, 2 pi. So we're over here, and we're 1 pi 6 less than that. So 11 pi over 6. So what's the cosine of 11 pi over 6? Positive. So it's going to be square root of 3 over 2. And the sine of negative pi 6, negative 1/2, so minus 1/2 I. And 4 to the 5th, do we know that? 1024. And we simplify this, so this is going to be 512 times the square root of 3 minus 512I. And we're set. Much easier than multiplying this thing out 5 times. Questions? This is a really nice thing to be able to do. And I don't know if I mentioned it the other day, writing complex numbers in trig form, You will see this a lot if you go into science or engineering. Use complex numbers to talk about circuits, to talk about current in electrical circuits. Use complex numbers in trig form to talk about fluid dynamics. It also comes up, I remember doing a lot with these things when I took my optics class when I was studying physics. So you talked about waves going through glass in terms of complex numbers and trig functions and complex numbers. So it shows up more than you would think. It seems like kind of an odd thing, but it shows up a lot. Quantum mechanics uses complex numbers. All right, questions? So what we're going to do next is take this idea of the powers of complex numbers and use that idea to kind of go backwards and be able to find roots of complex numbers. And this is nice because in the past, we never really had a way to do this, unless it was some kind of specific relationship that we knew, that we happened to know how the two were related. So we're going to say that, I'm going to call this U, some complex number, is S cosine beta plus I sine beta. And we're going to say this is an nth root of some other function z, or not function, another complex number, z equals r cosine theta plus I sine theta. So if this is an nth root, to undo an nth root, we raise it to the nth power, right? To undo a square root, we square it. To undo a third root, we raise it to the third power, right? So what this tells us is that to undo this third root, I'm going to say that u to the n equals z. So that tells us, so we're undoing that nth root. So if we raise this to the nth power, that's going to give us this thing. So let's write this out in trig form. We know what u to the n is. That's going to be s to the n times cosine n beta plus I sine n beta. That has to equal r cosine theta plus I sine theta. So if these two are equal, then s to the n equals r. The moduli have to be the same. So that tells us that s equals the nth root of r. And our moduli are just real numbers, so we know how to take the nth root of a real number, or our calculator knows how to do that. And that tells us that n beta has to equal theta or coterminal angles of theta. So we're going to write that as theta plus 2 pi times, I'm going to say k. And it's only certain multiples of theta, because we're going to say that k equals 0, 1, 2, dot, 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 to the n, up to n minus 1. Once we hit that many multiples of 2 pi, we start repeating. We get the same angle, we get the same exact answers. So, for example, if n equals 3, then we would go theta plus 0 pi, theta plus 1 pi, and theta plus 2 pi. So we'd get 3 coterminal angles of theta. And after that, we'd start to repeat. And this tells us that beta, the angle for our root, equals theta plus 2 pi k over n. So we're kind of dividing theta by n, so we're kind of undoing what we did when we found the power, but we have to deal with these coterminal angles. So we take the nth root to undo the nth power, we divide the angle by n to undo the multiplying by n, but we also have to take care of these coterminal angles. And that's what this k equals 0, 1, 2, up to n minus 1 does. And once we hit n, then our answers start repeating. So what this tells us is a number is going to have 2 square roots. It's going to have 3 third roots, 4 fourth roots, 5 fifth roots. And this lets us find all 2, 3, 4, 5, however many of them that we're looking for. All right, questions on what we've done here? All right, so we're looking for s to find our nth root. We're looking for s. So to find our new modulus, we would take the nth root of r, and to find our new angle, to find beta, we would have to use this formula to find our angle. No, it's not that bad. All right, so so let's write this out in one formula. So we're going to say that s, or that the nth root of r equals, or z equals, sorry. So I'm going to put this together into one thing, so it doesn't look so intimidating.
Yep.
The nth root of z equals r cosine theta plus I sine theta is the nth root of r times the cosine of theta plus 2 pi k over n plus I sine theta plus 2 pi k over n. So we're just taking the nth root of our modulus, and we're dividing our angle by n, but we're dealing with these coterminal angles. And we're going to say the k equals 0, 1, 2, up to n minus 1. So this is how we're going to find our nth roots. And I need one more set of parentheses here. Or one more to close that one off. So essentially what we're doing is undoing our power. We're taking the nth root of r. We're dividing theta by n. The only difference is we have to take care of these coterminal angles. So if we have a problem that has a third root, we're going to calculate the cosine and the sine of 3 different angles. One for k equals 0, one for k equals 1, and one for k equals 2. So this is how we're going to find our nth roots. So I just want to go through a couple of examples of calculating. It's not difficult, it's not complicated. It's just keeping track of your k. That's really the only thing that makes it a little kind of not difficult, kind of tedious, really. All right, other questions? Okay, let's go through a couple of examples. Let's find the fourth root. We're going to find fourth roots of 16. That's a U. All right, so up until now, if I said what's the fourth root of 16, what answer would you give me? 2. But we know there are 4 fourth roots. So let's find them. That applies to every single number.
So every single time you see a root that's over 2,
You should have however many. Right. So every number has 5 fifth roots. Every number has 6 sixth roots.
I've been mathing lies.
Right. So we're undoing some of the lies that you've been told, and it's not lies, but just that's not the complete truth. All right. All right. So let's write this in trig form first. So we're going to write this as a complex number in trig form. So this is 16, and I can say this is 16 plus 0i, right? So how do I write this in trig form? What's our radius? What's the modulus? How far away is this from 0? 16, right? The radius, the modulus of this complex number is 16. 16 units from 0. And what's our angle? Here is 16 over here on the 0 degrees. There's this number in trig form. The fourth root. So the fourth root of 16, or the fourth roots of 16, are going to be the fourth root of the real number 16 times the cosine of 0 plus 2 pi k over 4 plus I sine 2 pi k, or 0 plus 2 pi k over 4. And here k is going to equal 0, 1, 2, and 3. We'll get 4 fourth roots. We always start at 0, and we go to 1 less than our root. So what should one of these answers turn out to be?
0.
Wait, what did we say the fourth root of 16 was? 2. One of them better turn out to be 2, right? The thing we've been told all our lives better be true. We hope it is. Otherwise, we're in big trouble. All right, so let's do our calculation for k equals 0. K equals 0. What's the real fourth root of the real number square root of 16? What did we say it was? 2. All right. Cosine of 0 plus 0 times 2 pi, which is 0, plus I sine 0, equals 2. Thank goodness. We got our real fourth root of 2 out. All right, now we're going to do it for k equals 1. So the fourth root of 16 is 2. And then we're going to have a cosine of 0 plus 2 pi over 4. So what's 2 pi over 4? Pi halves. Plus I sine pi halves. What's and I'll write it underneath here. What's the cosine of pi over 2? 0. What's the sine of pi over 2? 1. I is one of our fourth roots of 16. What's that?
What happens to I?
Sine of this cosine of 0 is 1. Sine of 0 is 0. So we have 0 times I, which is just 0. This is 0. Sine of 0 is 0. So we're multiplying I times 0. All right, let's do let's do this for k equals 2 now. So we get 2 times cosine of 0 plus 4 pi over 4, which is pi plus I sine pi, which equals 2 times the cosine of pi is negative 1, and the sine of pi is 0. And I get negative 2. So plus or minus 2 is a fourth root of 16. And 2i, what are you going to guess the other fourth root, the other imaginary fourth root is? Negative 2i. Let's just do it just because it's nice, just so we see the process. Now k equals 3, so we get 0 plus 6 pi over 4, which reduces to 3 pi over 2. And this comes out to be, this equals 2. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is negative 1. Negative 2i. So there are our 4 fourth roots of 16. Now here's the really cool thing about this. Geometrically, in the complex plane, what this tells us. What's the radius of each of these? What's the modulus of each of these numbers? 2. All of these numbers, all of these roots are on a circle of radius 2. All of them are on a circle, radius 2. And how far apart in radians are each of these roots? Pi halves. What is 2 pi over 4? Pi halves. Each of the roots is on a circle of radius 2, and they're each separated by our original angle divided by 4. 2 pi over 4. Pi over 2 radians. So, and this will happen. Listen up. We're going to do one more example that doesn't have it quite as clean of angles, but this is always going to happen with roots of complex numbers. The roots will always be distributed on a circle with radius equal to whatever the root is of your real number, and they're always going to be separated. It's always going to be symmetrically distributed around the circle by whatever your angle is divided by the root. So they're going to be symmetrically distributed around the circle by whatever our angle is divided by the root. If that's how far apart each of the roots will be separated.
How many tests do we iterate all these out or determine that?
So here's what's going to happen. Well, we'll look at the next example. They're not always going to be this where all your roots are going to be on the axes. So it gets a little more complicated to calculate them out. But if you realize that you're just adding a multiple of your angle divided by your root number, you can do it that way. So that's essentially what we're doing here. Is we're just adding a multiple of pi over 2 to our original angle each time. All right, so let's look at another example. Whoops, I didn't want to do that. I have to wait for this to open and then we'll close it. Close. There we go. So let's find the 3/3 roots. The 3/3 roots of 4 square root 3 minus 4i. So not quite as nice a number, but it's not too bad. All right, so first thing we want to do is turn it into trig form. So our radius is going to be the square root of 4 square root 3 squared minus 4 squared. So this is going to be 16 16 times 3, which is 48. Thank you. Plus 16, which is square root of 64, which equals 8. So r equals 8. And then we know that tangent theta is going to be negative 4 over 4 square root 3. Then we have one similar to this. Negative square root of 3 over 3, and what quadrant are we in? Fourth quadrant. So what's our angle in the fourth quadrant with a tangent of negative square root of 3? So theta equals, very nice, 11 pi over 6. All right, so the third root of 4 square root 3 minus 4i equals the third root of our modulus times the cosine of, and on most of these it's probably going to be easier to calculate in degrees rather than in radians. It's easier to add those multiples. So 11 pi over 6, how many degrees is 11 pi over 6? 330. So we're going to say cosine of 330 plus 360k over 3. So instead of 2 pi, we're going to use 360. So we're adding our coterminal angles there. And then this is going to be plus I times the sine of 330 plus 360k over 3. And one more. And k is going to be 0, 1, and 2. So we get 3 third roots. All right, so let's do our k equals 0. What's the third root of 8? 2. Okay, so we get 2 times the cosine of 360 times 0 is 0. So we get 330 over 3. 110 degrees plus I sine of 110 degrees. And I'm just going to plug this into my calculator and calculate. So this is going to be negative 0.684 plus 1.88 I. So I'm just plugging this into my calculator because this doesn't give us a nice angle. And then we're going to do k equals 1. So we're going to say for k equals 1, we get 2 cosine of 330 plus 360, and we divide that by 3, and that comes out to be 230 degrees. So I just 330 plus 360 divided by 3, and I get 230 degrees. And I plug this into my calculator and calculate, and I get negative 1.29 minus 1.53 I. And then finally for k equals 2, for our third root, I get 2 cosine, and now I'm going to do 330 plus 2 times 360. Divide that by 3, and I get 350. And when I plug that in my calculator and calculate, I get 1.97 minus 0.35 I. And if I graph this out, this one doesn't turn out quite so nice graphically. These points all are on a circle of radius 2, and I get one, let me draw my circle in here. I get one down here. I get one kind of up here, and one over here. Yeah, yeah. And each of these roots is going to be separated by 330 divided by 3, or 110 degrees. So they're 330 divided by 310 degrees, so each one is separated by 110 degrees. Sort of. All right, questions there. This thing is pretty amazing. So roots of complex numbers have it kind of tells us the roots of complex numbers have something to do with circles. And strange things happen on the complex plane. If you guys ever get a chance, one of the most interesting classes I ever took when I was an undergraduate was complex variables. It's all about complex numbers. Really interesting things happen when you start working with complex numbers. All right, questions? Okay.
Are you sure you did the last one right? Because you said each one's supposed to be 110 degrees apart, and the second one was 240 degrees instead of 240.
It's 110 degrees from the first one. Let me write this down. Oh, I know what I did. It's not the angle divided by the n. It's 360 divided by n. Those to be 120 degrees apart. Yes. And the other one was pi over 2. That's 360 or 2 pi divided by 4. Yeah. So this should be 100.